Welcome to part 3 of robotic arm manipulation with human experiences and reinforcement learning. In this video, we're going to be setting up the buffer class. So here I've created a buffer.py, and we're really only going to need numpy. So let's go ahead and just import numpy as np. And then we're going to say class replay buffer. And this will be a little bit different than your standard replay buffer class because we're going to be including both some augmentation, so the ability to add some noise when we're pulling experiences back, as well as a poor man's version of prioritized experience replay to prioritize our human learning data. So let's get started. We're going to define our class, and that will have a max size, it will have an input size, it will have an actions, augment data equals false, augment rewards, so we're just setting some defaults to false for both of these things, and expert data. Here, let's go ahead and go down to the next line. Expert data ratio, we're going to default to 0.1. And augment noise ratio is going to default to 0.1. And then we don't need that none. All right. Here in our init method, we're just going to set some of these variables. So we're going to say self.memSize equals max size. Self.memCounter, memctr equals 0. Self.state, helps if I can type self correctly. Self.state memory equals np.zeros. Self.memSize and input size. And self.newStateMemory is going to be np.zeros. Hang on, I need to double those. Self.memSize again, and input size. Self.actionMemory is going to be np.zeros. Self.memSize and nActions, and then self.reward memory is going to be np.zeros, self.memSize. Important to note, these three have double parentheses because we are, passing in a multi-dimensional object here. For reward memory, that is just a single dimension array, so no double parentheses. Self.terminal memory equals np.zeros, self.memSize, and dtype is bool. All right, and then we'll do the rest of these. Self.augment data equals augment data, self.augment rewards equals augment rewards, self.augment noise ratio equals augment noise ratio, self.expert data ratio equals expert data ratio, and we're also going to need a self.expert data cutoff equals 0. All right. There are several places in the code where we need to be able to run the len argument on replay buffer. So we're just going to go ahead and override len so that, or provide a method for len. And we're going to define the length of this replay buffer as self.memctr. And then we're going to ask if we're going to need a can sample method. So I prefer to build functionality into objects to see if there's enough data to pull from them or see if something can interact. I don't want the external calling code to need to understand if there's, the internal workings of that class. So we're going to say def can sample. So we can ask the replay buffer and we'll pass it a batch size. And we're going to define can sample as if self.memctr is greater than batch size times 1,000. And this number would usually be lower for reinforcement learning. Usually you want to start training much earlier in the process. But since we're relying on human data as sort of a starter, and then later in fine-tuning, we don't want to overcorrect with small, replay buffer sizes. We actually want this to be fairly large, unless the memory is, batch size times 1,000, and our batch size will be 64. So unless we've got at least, 64,000 records here. And actually, for our human training, we may want this to be lower. We'll make it batch size times 500. That will need to change later in training, though, a little bit higher. So we're going to say, if self mem counter greater than batch size, then it can, then we want to return true. Else return false. All right, that looks good. Def store transition. So this is, storing something in memory. Self state action reward new state. Actually, let's call this next state. Done. And we'll go ahead and change this to next state memory. So our index is going to be self.memCounter modulus self.memSize. And what we're doing here is we're basically declaring a fixed size in memory, and then we are stepping through it with the index. And the index will always be, so, if our let's just kind of play that out. So let's say our memory is 50 units long. Index is 1. Well, or let's say our mem counter is 1. So mem ctr equals 1. So as we add, it's going to be mem counter 2, 3, 4, 5, all the way through 50. And that will result in an index of 50. Self mem counter 49% mem size, or modulus mem size, that's looking for a remainder. So a mem counter of 49 would equal index of 49. As soon as mem counter is 51, then that's now going to equal an index of 1. So what this logic does is it effectively lets us fill up the buffer, and then we loop back around to index 1 and fill it up from the start again. That is a more memory efficient and just processing power efficient way to do this than to create a list that's not a fixed size and drop an object off the front every single time. So that is what we are doing here. So we have our index. We're going to say self.stateMemory index equals state. Self.nextStateMemory index equals next state. Self.actionMemory index equals action. Self.rewardMemory index equals reward. Self.terminalMemory index equals done. And then we'll do self.memCounter plus equals 1. We'll just increment by 1. All right, now we get into some more logic here with our sample buffer. So this one will be fun. So sample buffer, self batch size. Max mem is the minimum, of self.memCounter and self.memSize. And we're going to, this is where we get into some of our experience replay. So we're going to collect a bunch of human data, and then we want the ability to force it to use more or less of that human data. So the way I solved this, and there are many ways to do this, this probably isn't the right one, but I did if self.expert data ratio is greater than 0, expert data quantity equals int batch size times self.expert data ratio. So if you have a batch size of 64 and you put in a 0.5 as your expert data ratio, this is going to return a 32. It's going to grab half of your batch from the expert data section. And that is also why we had our expert data cutoff up here, because we want to tell it on data load what that expert data cutoff is, where the expert data stops. You could also label it. That's not how I did it in this scenario. And some of that is just how I built up the problem. I got all that expert data, and then I figured out later that I needed to prioritize it. So I used a cutoff value instead of labeling it as I went. You could also do something like label expert data as you build it, and then select based on that label. But again, not how I did it. So I'm going to say random batch is np.random.choice maxmem, and then we're going to grab a batch of batch size minus expert data quantity. So again, if this ended up being 32, then this batch size minus expert data quantity would be 32. So we're guaranteeing we still get a full batch. So I'll say expert batch is equal to np.random.choice, and that's going to be self.expert data cutoff and expert data quantity. So that's basically saying, hey, I want a up to expert data cutoff in this. So I want something, between 0 and this, and I want it to be, 32 long. That's what that's telling us. And then we're going to say batch equals np.concatenate and random batch and expert batch. And then down here, we'll have an else, and that's going to be batch equals np.random.choice maxmem batch size. All right. Now we will pull our states is self.stateMemory batch. Next states equals self.state next state memory batch. Actions equals self.action memory batch. Rewards is self.reward memory batch. Dones is self.terminal memory batch. All right. So that would be most of a basic buffer class, but we also want to do some data augmentation and some reward augmentation. Couple of reasons. Data augmentation, adding some noise to the data, actually makes training more stable. And then I noticed that if you augment the rewards, and I don't mean adding rewards as it gets closer to the target, I literally just mean making the rewards that it does get numerically larger. It seems to learn better. I don't know why that is mathematically. If you are more familiar with it than me and you'd like to comment, please do. But adding a larger reward seems to equal better results. So we're going to go ahead and say if self.augment data. So we'll say state noise std equals self.augment noise ratio times np.mean np.abs states. So we're grabbing the noise based on the ratio times the mean of the absolute value of states. And then we'll do the same thing, action, noise rate, noise STD by actions, and reward. And we're actually not going to use rewards noise, so I'm actually just going to leave that one out. And then we'll add our dynamic noise. So states equals states plus np.random.normal 0 state noise std states.shape actions equals actions plus np.random.normal 0 action noise std actions dot shape. Okay, so that's our data augmentation, and then we'll say if self.augment rewards, and this one's pretty simple, rewards equals rewards times 100. I did get some interesting mixed results also by making all negative rewards or all zeros a -1. And the easiest way to do that, and I'm not going to leave this in so you don't have to type it, I did like a rewards equals rewards -1. And what that did is it made all of the successes 99s and all the failures -1. That got good results in some cases, but it didn't work well all the time. So I just went ahead and left this at self-augment rewards, rewards equals rewards times 100. And then finally, we're going to return states, actions, rewards, next states, and dones. And that completes our sample buffer. Finally, we are going to need to be able to save to CSV and load from CSV. That's not always a part of these kinds of problems, but in this scenario, we need to capture a bunch of data from a human, and we need to save it for the machine to pick it up and read, which means the ability to dump that data in some kind of standard storage location. So we're going to define save to, give myself another space there, def save to CSV, self, file name, np.savez, file name, state equals self.stateMemory to self.memctr, action equals self.actionMemory, self.memctr, reward equals self.rewardMemory, self.memCounter, just like we did before. Next state equals self.nextStateMemory, self.memCounter, and then done equals self.terminalMemory, self.memctr. All right, and then we'll just print out some output. Saved, file name. Okay, and then finally, the last method we need to define, def load from CSV, self, file name, and we're just going to leave it there. Okay. Let's see. We do need one variable. We need expert data. Data equals true. So here we're going to do a try. Data equals np.load. File name. What did I mess up? Oh, yep, you have to actually put, have to go to the next line there. It won't work like that. And I'm going to go ahead and throw in my except for the pass, so it'll stop complaining at me in the syntax editor, or the syntax checker. So self.memCounter equals len of data state. So we want to go ahead and get our new memCounter. We want to get our state memory up to self.memCounter equals data state. So basically everything we just did in reverse. So I'm going to copy that a few times. We're going to say action memory is going to be data action. Reward memory is going to be data reward. Next state memory is going to be data next state. And self.terminal memory, self.memCounter is going to be data done. All right. And then here we will print successfully loaded file name into memory. And then I like a little output that tells me self.memCounter memories loaded. All right. If expert data, then self.expertData actually, I don't even think we need that. I think we just need to set self.expertData cutoff equals self.memCounter. And the reason we're doing that is if it's expert data, then we want to go ahead and set that so that it can weight it properly. And if it's not expert data, then we really don't care. We just want to, treat it like any other batch of data that you might have. And then we'll finally throw in our except print unable to load memory from file name. All right. And the reason we even care to do a try except here is, sometime for the first run, there might not be anything, there. So our two options are to either do a check first and say, hey, is the file present? And then do a load from CSV, or to do a try catch. Okay, try to load the data. If you can't load the data, then just go ahead and start a brand new buffer. So back over here on humancontrol.py, we are going to go ahead and load up or create our first buffer. So I'm going to say state size equals state.shape 0. We need some data. And then we're going to need a few more parameters up here. So we're going to need a replay buffer size equals 1,000,000. That's a good place to start, just in general. We are going to need and that may be all we need. Here, let's go ahead. So we've got state size, and we're going to say memory equals replay buffer. Oh, we need to import it up here at the top. From buffer.buffer import replay buffer. So now memory equals replay buffer. We can feed in a replay buffer size. We can say input size is state size. And n actions is env.actionspace.shape 0. So we're pulling that live from the environment. And then let's go ahead and run this and just make sure it doesn't fail. Hey, definitely default except must be last. What did you not? I left my accept pass in there incorrectly. Okay, and that's the error we expect. That one is not, though. So state size is state dot, so none type attribute does not have, has no attribute shape. So let's go take a look and see what it doesn't like. So state shape, human control, line 24. So it doesn't like that I try to do a state.shape there out of env.reset, which means something is going on over in our environments class. Something's a little off over here. So let's go take a look. We're doing, so in reset, we're doing self-env reset. We're doing a process observation. We're returning observation and info. Here, we're doing obs pause. All of that looks, here's the problem. We never returned observation concatenate. So of course it has no shape. It is literally a none, which is why it gave us the none type object error. Okay. So that is actually what we expected. This is being thrown because we're not, you know, the environment is not closing out. Let's see if we can just get rid of that with env.close. There we go. All right. So we now have our memory. And if we go ahead and try to load, so this should fail, but it should fail cleanly. So we should say memory dot load from CSV, file name equals checkpoints, if I could spell, slash human memory, and this is where we're going to use that tasks no spaces dot npz. So this won't be here. Oh, and you will need to go ahead and create a checkpoints folder. So let's just, and it said unable to load, and that is exactly what we expected. So I think this is probably a really good place to stop the video, and in the next one we're going to start working on our controller.py to actually take in data from a game controller and pilot our robot. So see you in the next video.